If you really want to understand the world around us, from the pull of gravity to the path of a ship on the ocean, you've got to learn the language it's written in. And today, we're going to learn a key part of that language, vectors.
And I'm not the first one to say this. The great astronomer Galileo Galilei, he said it centuries ago. He basically said that to really get a handle on reality, you have to look at it through the lens of math. And what we're going to see today is that vectors are one of the most powerful characters in that entire language.
Okay, so let's dive right in. Think about it. There are basically two ways we describe stuff in the world. The first one's called a scalar. Super simple. It's just a number. 5 kilograms, 20 degrees Celsius. Done. But what if you're pushing something, or you're trying to track a car? Just saying 20 kilometers per hour isn't the whole story, is it? I mean, if you're trying to meet a friend, you need to know which way they're going, right? And that is where vectors come in. 20 kilometers per hour, north. That little piece of information, that direction, it changes absolutely everything.
All right, so let's properly introduce the star of our show. What exactly is a vector, anyway?
And you know what? It's beautifully simple. A vector is just any quantity that has both a magnitude, which, hey, is just a fancy word for its size or its length, and a direction. It's the thing that answers two super important questions: how much and which way.
And that leads us to the absolute perfect way to picture one in your head. Just think of an arrow. The length of that arrow, well, that's its magnitude. So a stronger push means a longer arrow. Makes sense, right? And the direction it's pointing, well, that's its direction. It's so simple, so visual, but unbelievably powerful.
Okay, so like any good language, vectors have their own grammar, right? There are rules for how you can combine them and work with them to describe more complicated stuff.
And that brings up a really big question. Imagine you're walking forward, but there's also a strong wind pushing you from the side. Where do you actually end up? In other words, how do you add two vectors together?
When you're drawing it out, it's actually a piece of cake. We use this thing called the tip-to-tail method. So first, you draw your first vector. Let's call it A. Then you take your second vector, B, and you stick its tail right onto the tip, the pointy end of A. The grand total, your result, is a brand new vector that you draw from the very beginning of A all the way to the final tip of B. That's it. That's your combined vector.
And check this out, because this illustrates a really cool property. Think about it. It doesn't matter if you walk a block east and then a block north, or if you walk a block north and then a block east. You end up in the exact same spot, right? Well, it's the same with vectors. A plus B is the exact same thing as B plus A. The order doesn't matter one bit.
Okay, so drawing arrows is awesome for getting the idea in our heads. But let's be real. If you're building a bridge or coding a video game, you need to be precise. You need actual numbers. So how do we turn these pretty drawings into cold, hard math?
Well, the secret is to put our vectors on something we're all familiar with, a grid, a coordinate system, just like a map.
And here is the absolute key idea. Any vector, I don't care which way it's pointing, can be broken down into simpler little pieces. We call them components. Just think about it like this. Instead of describing a diagonal walk in one go, you can describe it by saying how far you walked east-west and then how far you walked north-south. We're just swapping that one diagonal arrow for two simpler ones, one horizontal, one vertical, that get you to the exact same place.
And honestly, this is a total game changer. Why? Because it means we can stop doodling arrows and start representing a vector as just a simple list of numbers. So you can see here, vector A is no longer some abstract arrow, it's just 2, -3, 7. That tells the computer or an engineer exactly how far to go along the x-axis, then the y-axis, then the z-axis. It is clean, it's precise, and it's incredibly efficient.
And here it is, the big payoff, the reason we do all this. Adding vectors with components is, well, it's ridiculously easy. Seriously, forget all that tip-to-tail drawing. You just add the x parts together, then you add the y parts together. That's literally it. We've turned what looked like complicated geometry into super simple grade school arithmetic.
Okay, enough theory. Theory time is over. Let's put these tools to the test and see how they can solve a real, honest-to-goodness, high-stakes problem. Let's talk about a rescue at sea.
So here's the scenario. You've got a central checkpoint like a lighthouse or a buoy. From that point, a Coast Guard ship is 35 kilometers away in one direction. At the same time, a sailboat is sending out a distress call. And it's 20 kilometers away from that same point, but in a different direction. So first things first, we've got to translate this real-world problem into our new vector language. We'll decide that the checkpoint is our origin,
are 0, 0 on the map. That means the Coast Guard ship's location can be represented by one vector, and the sailboat's location is a second vector, and they both start from that same origin point.
Okay, now for the million-dollar question. What's the direct path from the Coast Guard ship to that sinking sailboat? Well, guess what? That path is just another vector. And to find it, we do something super simple. We take the sailboat's position vector and we subtract the Coast Guard's position vector. The answer will be a vector that points directly from the rescuers to the boat.
And this is why we love components. This is where they are king. We've already figured out the east-west and north-south components for both boats, so now all we have to do is subtract. For the east component, you take the sailboat's 16.2 and you subtract the Coast Guard's negative 26.0. That gives you 42.2. You do the exact same thing for the north component. Just like that, the math gives us the precise components of our rescue path.
So, we have these new components for our rescue vector. What do they actually tell us? Well, first, we can use them to calculate the magnitude. Remember, that's just the length. And in this case, the length of that vector is the actual distance the Coast Guard ship has to travel, and that distance comes out to 55 kilometers. But look, distance is only half the battle, right? Knowing you have to go 55 kilometers doesn't help if you don't know which way to point the ship. A rescue ship needs a heading, and guess what? Those exact same components give us the precise direction. The course they need to set is 40 degrees south of east. Distance and direction. With vectors, they now have everything they need to save the day.
I mean, that rescue at sea is a perfect example of just how incredibly powerful vectors are. And it's not just for boats, not by a long shot. They are the absolute bedrock, the fundamental language of physics, describing things like force and velocity. They're what engineers use to design bridges that can handle wind and stress. They're what graphic designers use to build the amazing 3D worlds you see in video games and movies. And yeah, they're what the GPS in your phone is using right now to get you from point A to point B.
The truth is, vectors are this kind of invisible code that's running the show all around us, governing motion and force. The push of the wind on your face, the perfect arc of a basketball heading for the hoop, even the simple force of gravity holding you in your chair as you listen to this. You've just learned the ABCs of this secret universal language. So my question to you is, now that you know what to look for, where are you going to see them next?